Oh yeah, everything here in your handle, you gotta write this thing, just start, right? Kind of fix it up, just on the full corner, right? Right, so the first thing we have to run over, we have to run over all the quantities in electricity, right? What were the three main quantities?
I, R and A.
Current, resistance,
Voltage.
right? What was current again? Tell me what's current again? Current is what?
Yes.
Right? So current is a fundamental quantity and in such it cannot be derived. It's the flow of what? It's basically the flow of electrons, right? Right? These charges will be positive and negative and so on, right? The magnitude of current is numerically equal to the rate of flow of charge, right? So that leads us into our first definition, right? I is equal to QMT, right? And the SI unit is amperes. Okay? Well, sorry, here's the writer. Right? As I go along with you, you can make your own little summary, right? Only little formula, right? Huh? What are you for? Right? The direction of conventional current flow is taken as that which is net displacement of positive to negative, right? So all that's saying is this conventional flow is from positive to negative. High to low potential, right? Please remember the only way current will flow is if there's a change in potential from high to low. What would happen if there was a equal potential? Current will flow, right? Okay, so there must be a potential difference, right? Positive to negative current to flow. Electric current can be measured using a ammeter connected in series, right? Ammeters are connected in series. This means that the ammeter must have a very low internal resistance, right? So just to remind you, the ammeter is connected in series. Huh? Oh, sorry. Right? The ammeter is connected in series, and the ammeter has a very low internal resistance, right? Why? Why, Arian? Huh? Why does the ammeter have a low internal resistance? The ammeter itself. Because remember when you measured current, right? They want current to flow through it. But the voltmeter has what? High internal resistance, right? Right? Electric charge. The electric charge would flow past a point in a given time when a steady current flows the product of current time. Right? Q is equal to I T. SI unit in coulombs, that should be capital C, and that's the definition, right? Potential difference, SI unit is V. The potential difference between 2 points is defined. Very important. Underline. If you can underline, right? Potential difference is when electrical energy is converted to other forms per unit charge. Electric energy converted to other forms per unit charge. So I have to pay attention.
Yeah, just one second. That's sweet. You say something every class.
Electrical energy converted to other forms per unit charge. Okay? Right? Electrical energy from electrical to other forms, right? Per unit charge, that's the definition for electric potential, right? Are you okay with that? Right? Something that we didn't really focus in Form 5, something called oh, lower down. I just skip it now just for 1 minute, right? How do we define EMF, right? And look at the definition, look at the difference in definition EMF and definition for potential difference, right? Right, the EMF of an electrical energy source is defined as the energy converted into electrical from other forms per unit charge. Right, remember EMF is like the total energy being supplied, right? Remember that? The EMF kind of comes somewhere. Where the EMF comes from the supply, from the source, right? So basically, your potential difference is when electrical energy is converted to other forms per unit charge, while EMF is electrical in other forms of electrical energy per unit charge. Okay, so that's something I want to understand, give it the differentiation between them, right? Potential difference in the electrical to other forms per unit charge. EMF is other forms to electrical per unit charge. Okay, so we have to understand when we gain EMF and when we actually gain PD. Where you will measure PD, right? We said that we will get EMF from the source, right? But where you will get PD? Across what? Across a load, right? Something that's using electrical energy. Right? So across the load, you'll be able to get PD. Right? So because what you say, right? Tell me what this voltmeter measures. And tell me what this voltmeter measures.
So I'm like, and also be.
That's a piece of it. What's that? We're not measuring any source, but of course, if it open. If you measuring what? EMF or PD? The one on top, the one on top is from the source, right? So if the circuit open, you're measuring EMF. And the one underneath here is PD. Right? So now we're gonna look at the length of, by the way, are they the same? They will be the same value?
Distance, I will have a rubber distance.
Alright, okay. I can kind of pass for now. Right? Earlier, you can now look at the length between this and this. Right, let's just go down back here. Resistance. Any questions online, Tavisha? Are you okay? Right, resistance, the resistor conductor is defined as the ratio of PD. Alright, nice. It's defined as the ratio of PD across the conductor to the current flowing, right? So we know R is equal to V on I, or we know that V is equal to IR. SI unit, ohms, right? Right, the ohm is the resistance of the conductor, and they gave you the definition here. Next page.
This is starting from this. Sorry.
I know, that is the second page. We now want the definition. Alright? Alright, nice. Here's what we're looking for now. We're looking for a relationship between internal resistance, terminal PD, and the EMF. Alright? So we want to understand the difference between internal resistance, terminal PD, and EMF.
That's why it's called pretty long.
When I say thermal, there's a thermal.
But that's what's like.
Terminal, right? Look at here. I want you to really note and see these things. You really know.
So that.
Right? So we're trying to get a relationship between terminal PD, EMF, and resistance. Alright? So let's jump to this. Let's see if we can put it together. Alright? So Kishara, inside the battery, you gotta recognize when it connected to battery is get hot. Yeah, so what that means I lose energy, right? So the reason why battery becomes hot is because it has internal resistance. Alright? So we are trying to develop now a relationship between internal resistance, EMF, let's call it E, the load, sorry, and voltage here. Right? Let's see if we can put that together. Current to the circuit is what? Let's call it I. Positive, negative. Remember the voltage? Remember the long is positive and the short is? They are not the same height. And thickness, one thicker than the next one. Alright. So, what do we know about EMF and TD again? What do we know about this value and this value? Not the same. Who larger? EMF, right? So we know that the EMF is equal to the V load for the extra load. Very good. Plus here, the extra going there. So the energy being supplied here in Taylor, being lost here. Right? To the internal systems. Okay? All okay with that?
So that is just like help you understand.
Yeah. But relativity resistance is the conversion from chemical to electrical. Right? And now it's perfectly efficient. Right? Yeah. Right, yes. So it will be I by R internal. So therefore, the EMF being supplied is being used by the load and being used by the internal system. Whose law is that? Whose law is that? Energy being supplied is being used by the internal and the external load. You can't say that. What would I imply some of them? Okay, what's conservation is that?
Conservation energy.
Energy, right? Energy being supplied is being converted into. Should we do a thing like that? I don't see it in right? Alright, so the energy being supplied is equal to the energy being used by the load and energy being used by the internal system. Alright, so EMF is equal to I by V plus I by small r. Right? That's the more familiar formula, right? E is equal to I by R, and you can factor out the I. That's it, right? Yeah, but you have the conservation energy from one. Energy is converted from one. Alright. Let's make a note of that, right? That's the relationship between EMF, terminal PD, and internal resistance, right? Ranju, are you okay with that? Are you okay with?
So what you want to start?
Alright, so everything I just talked about, right, in this little formula here, right? Okay, that's the concept. Right, chemicals within a cell causes a resistance current flow. The resistance is called internal resistance of the source or the source resistance. The internal resistance is in series with a cell and
I'm sure I don't mind. She should be proud.
I'm electrical. And my father listen to that part. I mean,
That's like.
right? The terminal. Only
Okay,
this
that was
one,
not me, that was not me. Okay, wait, yeah, but literally. No, no,
right? The
no.
PD measured causes the terminal of itself to be called terminal P,
But like,
right?
it's not
Right, right, there's something important, right? And I wanna prove this, I wanna show you this, right? Are you ready, Nikolai? Are you ready? The PD measured across the terminal of the cell is called terminal PD, right? This PD depends on the size of the current being drawn from the source. If the current, if zero current is drawn, that is the source is open, then the terminal PD is the EMF. Here's what it's saying, right? If you have a source, right, and the circuit opens, right, and you connect a voltmeter here across the source, what you are really measuring is the EMF, right? Yeah. Okay. So sometimes we call it the terminal PD itself, right? But the EMF comes from the source. Alright, if you close the circuit, the value will change, right? Right? Not all the energy supplied by the source is used in the external circuit. Some is converted to heat as charge flows through the internal system. The terminal PD is therefore not equal to EMF unless it is measured when there is no flow of charge. Right here, here's what I was talking about at the beginning of this. Consider the conservation of energy. Energy supplied by the source per unit charge is equal to the energy used by the external circuit per unit charge plus the energy dissipated as heat, right, per unit charge. So here, this is your EMF, this is your terminal PD, and this is your current through the internal system. All right, or you can write it like this: E is equal to I by big R, I by small r. All right, so this is the relationship between EMF, voltage, and internal resistance.
If we draw a graph, right? We have to be angry.
If you draw a graph of what?
E versus R.
Yeah.
Yes, sir. My example real has real problems. I think I'm back to the job. I get him now to the job, but I got my one. Yeah. You know what? I love video. That's it. Each hour, each. One. I come from Aryan, Aryan from and Aryan is no, I come from me. So you come from Aryan. Well, I'm following it wrong.
Just one thing I want to show you here. Watch this here. If we use the formula, and from the formula we make I the subject, yeah, look like that, right? Right, and watch closely here. Right, as R goes to infinity, what will happen? As the denominator goes to infinity, current goes to zero, right? And we know that when current goes to zero, V is I. V is equal to E, sorry, V is equal to E. Follow clear up? What here? What's the next part here? Right? If I were to plug in infinity here and infinity here, technically they'll cancel and you'll get one. So it means when R goes to infinity, V is equal to E. Right? So in short, when I goes to 0, V goes to E.
E is
Are you okay
EMF,
with that?
right?
And
E is EMF.
E is EMF and V is terminal V. That's okay? Let's try some small questions now. I have no answers to we are working about, right? Really easy, just changing the formula wrong. Let's try again. Let's try 1, 2, 3. No. No, so keep it all here.
Oh, you're failing dramatic.
Oh yeah, try that please.
So you people.
Oh yeah. Open up please. Yeah, that's it. Put on one side.
Yeah, but like.
Oh yeah, number 1. Oh yeah, put it, address simple.
It's too loud, sorry.
So you like it, look like it, you like, if you like it. That, you know, that, yeah, yeah. If that way, I'll get it. And somebody got up.
Somebody had asked me.
Yeah, but I know it's not up away. I saw that.
The other way was the other way. Remember last year we had 2 weeks back last year.
Yeah. Oh, we have to, that's not.
Collected or yeah. Collected, you know, 1 war.
Yeah, now it's okay.
Yeah. E is equal to B plus I. E is equal to I.
Right, like we will the solution is not. Yeah, I mean, the team.
Yeah. But it's not. Yeah, but I'm.
Dari ako, tayo masakit. Kaya sa tali. Kaya hanap ko rasa din. Rasa din.
Sunday, Iman.
You see, it's probably.
Saturday, yeah, po, 2 months, 8 months.
I don't think it's started to what you have this movie.
Can I correct number 1? Yeah.
It's 2 separate.
Yeah. Right answer them.
Yeah.
Right, how long?
I was trying to figure it
Right, number 1 is what?
Oh, yes.
Right, number 1, nice and easy. P is equal to terminal PD plus I by R.
That's plus.
Terminal PD is 12. Sorry, EMF is 12. Internal resistance is 0.5. current being supplied is 3. They want the terminal potential difference. So B is equal to 12
1.5.
minus 1.5. Number 2. Well, next one.
Next one.
That's our.
People love it online.
Wait, we're getting three answers.
0.5 volts.
Oh yeah, work out number 2 and number 3. Right, that's right. How B equal? That's. Alright, cool.
You're gonna get a little, you're gonna, that will have time to you look at me. Oh, you know what's fair.
I have work out number 2 and 3.
Like, it's an idea. It's an idea. You say it's. Easy for the.
Check that.
R is yeah, big R is the external resistor, small R is the internal.
Yeah. So. That belongs to that.
Should I again, sure?
Like, honestly, I.
Right.
Sit, I'm telling you, that's not too long, because I can't hear.
Number 2. Itself, they give me the EMF. Right, what they give me the EMF from 6 volts, they give me the terminal potential difference, and they give me current, find the internal. Very easy, right? Just plug in the values.
Yeah, that's me check out.
6 is equal to 5 plus 2 by R. So I got R to be a half. Yeah, R is a half, right? Number 3.
So we do that one still.
Oh, number 3 pass. Sorry. I'll try to mess it up. Not much to do wrong. Okay, yes, that I told you. When was wrong with it? Yeah. I think I'm gonna do wrong.
Basically, something else.
Anybody got that? Who out there?
Yeah.
Alright, that was the introduction, right? Try number 4. Try number 4. Right, remember, this module is electrostatic, electricity and magnets, right? So we're working on electricity for the rest of the month. Well done.
No.
Higher time power delivered again, higher time power delivered. If you check 2 pages down, I gave you all those formulas. P is equal to IV and power loss is what? No,
But I be very good.
PI squared R, right? Give me that with the one.
What? Oh, which one?
I squared R, power loss. You got done?
Yes.
Primitive of firing.
Oh, I what's that? Oh, I what's that? Oh, I what's that?
What?
What? Oh, I what's?
What?
Yes. Yeah, what?
Is knowing somebody old that? See it? See it? For the haircut.
I get hard.
Serious.
Ready?
Wait a minute.
Alright, online, you all done? From Kevisha, anybody else online? Finish? Kyra, Orion, you all getting through? I'll undo it now, right? I didn't see it. Alright, let's go. And then let's jump into that part before. First thing first, they gave us EMS, they gave us internal resistance. Current in the circuit, right? Calculate terminal PD, V is equal to E minus I by R. How much y'all got? 200?
Yeah.
200 or 380, right? Yeah. Power delivered by the motor. P is equal to, right? I is how much again? I is 100 and by 380, right? I swear I was power loss. Right? I would have been 100 squared by R. Small r is 0.2. Thousand, right? Okay. Right, so that was just the intro. Let's try to pass people. Kitchen, right? Panaya. Gabola, right? Yeah. Right, is not the best. Alright, this question, they gave you a circuit and they wanted to prove that. No value, they just a proof. Right, alright, think back here, right? RL is equal to IL to the minus 1 VB minus RL. Go ahead, use that circuit and prove that, please. This is RI here, right? L. Huh? Yeah, you can join if you want, but you can't get out proof. Same thing we do it, don't get confused with all the letters and thing, right? It's the same thing that we do in then. Let's see what tell you again. Banaya. And Banaya smile is like go.
So like that.
Up.
You can say, yeah. Yes.
Hurry.
That was being a plan for a field station.
That's very good.
Makes up to you.
Yeah. Like, also,
I think hey, we try to write up in order with the Sunday.
No, coach up, exactly what we just did. Identify what is the EMF, identify what is the terminal and so on and work it out. Just like what we just did, right? Oh, you have Shibish.
Oh, yeah.
The thing in red.
Right, going so right. So yeah, that could be.
Right, don't overthink it, right back the same formula we just did, and just write down what each quantity is.
Minus.
Write down what EMF. Same thing, same formula. Look at the circuit, internal resistance, supply. Online if you get it, must QED, right? Start from what it'll be equal. Yeah, you have to prove that. You have to prove the formula in red.
Well, accelerate this.
Prove the formula in red, starting from what you know, right?
Yeah.
If you get it, just mention QED. So what year is this? Earlier, you're right there. I don't know what year it is.
Yeah, that. Yeah. Yeah, we can have about real what's better with us.
The ship is back at the top.
I feel it's talking higher.
Wait, on me, you have to George, right? See, now, but the light is. Here on, and you say it, but all you know. Yeah, from well.
Yeah, nothing we had one, so that's great.
You ready?
Wait,
Wait, okay, give me a minute again. There you go. You lost? Right, you are helping. Right, so just think about it like this, you know, B is equal to. B is equal to I by big R plus I by small r. What you have to figure out is what is B? What is B in this case? Good letter. Actually, I should not be. Let me put it. I should not, sorry. What is E in this case? Okay. Look at it, circuit. What do you think is I? Sorry, what do you think is E? What do you think is the supply to these circuits? Yeah, PV, nice. What's the current in circuit? IL. What R? What's big R? What's the resistance of the external circuit? RL. RL. No, zero. R. Right? And what's small r? R. R. Right? R. Yeah, we did. The next part, well, I can understand it being like maths, it can be tricky, right? But the next part is you have to make RL the subsequent equivalent. After I get this.
And it was the numbers I, sir.
Sorry?
It was the numbers I,
Yes, sir. Right, make RL the subsequent formula. Right, so what you can do is you can make IL the subsequent formula. Carry across the IL, so you'll get BBIL to the minus 1 as RL plus RI. Then make RL the subject. RL is BBI to the minus 1. Okay, and that's it. You walk in more.
Yeah.
Wait, it's not in there.
So we let's have pictures of the time and but you don't have a bed, no?
So I'm gonna get a bed.
Still got mouse.
Wait, attention, I'll be the-
No, and you can from that. Yeah, the market spots are being comparable as well as those.
Was it one? I thought nobody should roll there, too early.
Technically. Include.
All right, nice. Everybody okay with that? Of course, suppose they ask Nikolai to plot a graph, right? Plot a graph of RL versus BP. All right, let's just say they ask me to plot a graph, right? But you know what the gradient is,
1 IL.
right? So you remember put it in the form y is mx plus c, right? This is your y, this is your x, so this is the gradient. This is your y-intercept, right? Getting the habit of doing that, right? All right, let's go again. Let's just squeeze in one more and then we can look at your philosophy. All right, let's take a look at your philosophy. Economic graph. Let's take a look at drip velocity, right?
Yes, yeah.
Right, all right. So, before we look at drip velocity, there is one more quantity that we have to know, right? All right. Before we look at drip velocity, right, there's a quantity that we need to know called resistivity. Watch it there, right? It's a kind of funny looking piece. Yeah, something like that. Right? But it looks something like that. Okay, look at it. All right, so electrical resistivity of a conductor at a particular temperature with a cross-sectional area. Oh, that should be out. So the electrical resistivity of a conductor at a particular temperature with a cross-sectional area of 1 meter squared is numerically equal to the resistance per unit length. All right. So this new quantity that we call resistivity is equal to resistance by area all over length. Right? And of course, if we rearrange the formula, we'll get resistance is equal to resistivity by length all area. Right? And you all may or may not have remember that if you use more wire in your circuit, what does that increase? Resistance. See why? The resistance will increase if you use a longer conductor. Right? Of course, if the area is small as well.
Yeah.
Okay. All right, so that's a new quantity that you need to remember. Resistivity. What's the SI unit?
Yeah.
Resistivity is ohm meter, right? Not per ohm meter. Ohm meter. All right. So that's something that you need to know, right? If you see resistivity, you know how to find it. And here, watch here. Here's a list of formulas that I should know, right? Nothing here is new, right? Nelia, nothing here is new. Pardon me? RE over RE over, oh, for which one? RE over L. Length of the conductor. Right? And here, we have a list of all the formulae that you should know from book by, right? Right? Once you remember this and this and this, you can figure out all the others. Right? All the others come from those. Okay? So you technically only really have 3 to those. I was trying to show you how to substitute one to the next, right? All right. Before we do drip velocity, let's see if we can get one small question on resistivity. All right. I don't have it. What's the answer here? Shivish, what's the answer here? Number 2. A, B, C, or D? Huh? Very good.
So the first one.
Yeah, we got a new party that's now, right? Right? We got a new party that's now. Do part B, please. Do part B. Huh? Right? Part B. Yeah. Right, just do the first part. Sorry, the second part, yeah. This. Try that part. Right, and then we'll do that triple of thing, right? No, I never, like, I never. Alright. I never.
Yeah.
Oh, some people miss one. Right, so they gave you resistivity, area, and power. Right, so we get current and length of the wire. Next, deviation. We can next deviation. The current flowing through the wire is I. Please define I. So look at what they give you. They give you area, they give you voltage, 110, and they give you power. So you identify by I and then you got part one is I. Current. Write down what the quantities they have first. Right, write down all the quantities that you have and then try to work it out, right?
Like it gets so bad, like because like started.
And you have P, you have P, and we have P.
Yeah, but if you look at that. Yeah, sure. Yeah. I don't think so. Yeah,
.00 by 10 to the minus 7.
Right now, I have to talk. These are the iron. No, yeah, like, I did that better.
All right. So they want us to get I and they want us to get
Yeah.
right. So to get I, you should use what? P on V, right? So that'd be 5,000 over 110. Point four six.
It's 4.5, so I approximately.
All right. 45.5 amperes, right? And then we have resistivity, we have area. So we could use resistivity as R, A, and L, right? So length will be R, A all over resistivity. R is how much?
Yeah, but use the iron.
Right, so we had to use B is equal to IR to get R, right? Which is B on I. Right, so R is where's B? 110 over 45.5. Area is 2.6 by 10 to the minus 6. So I'll work out R1 time here, right? All over resistivity, which is 5 by 10 to the minus 7. 12 points. Okay, nice. Last thing, just one more thing. I want to explain on video.
Fresh next week. And when class is finishing?
But that's anything like
This Friday class.
November.
Yeah, November.
Thank you.
Yeah, we have no exams, so.
November. Right. So you want to talk about something called drift velocity, right? So let's say you have a conductor, right? And in the conductor, we know we have electrons, right? But when we connect the conductor to a circuit, if the current flow in this way, the electrons will be going in the opposite direction, right? Because remember, electron flow is the opposite to conventional flow, right? And the average velocity, of all the electrons is what we call the drift velocity, right? This here has a cross-sectional area, it has a volume and so on, right? I think it have a length as well. Everyone prove it, Arya? So what Arya wants to come and prove? Well, not prove really, but come and find the formula for drift velocity. How we doing now? Wait, but before we do that, we have to define a few things. So I gave a cross-sectional area. What else you need? Right? Well, we'll find I later on. Something else we need. So we need a few things inside it. We need to find a way to get the number of electrons, right? So we have something called charge density. Charge density is small n. Small, No, we share. I just want to give you these things first, right? So charge density is the charge over the I find density. Mass and volume, right? So charge density is the charge over the volume. That's okay? So if I wanted to get a current flowing in the circuit, current is what? Charge divided by time. How will I get the charge of everything here? How will I get charge of everything there? The number of charges by charge or the charge. Or we could just kind of rearrange it. Oh? That's not good. But let me try with all the same letters I have in the new. Let's try to do it. Right, I have volume. Oh, this are the other way. Let me do it this way. The same thing, though. It's the same thing.
What I say?
All right. So if I use I just want to use what I was using in those, right? So here we have to follow with us. All right. So watch this here. So I want to get a current flowing in the circuit, right? To get a current flowing in the circuit, I need the total charge. Okay. So the total charge based on what I have here, the number of charge carriers. You're watching this, right? The number of charge carriers, right? That's the number of electrons. Number of electrons is the charge density multiplied by the volume. You're saying that? So the number of charge carriers is the charge density multiplied by the volume. And then if I want to get Q, I'm going to multiply the number of electrons by the charge of one electron. And this will give me the overall charge. Okay? So if this is the overall charge, I can say that the current is equal to NAL on E divided by T. Right? T to cancel, no, that's it. What you say? If an electron were to move from here to here, right? So if an electron moves from here to here, the length covered L, right? And what is length divided by time? Speed. And that's speed. Yep. So I is equal to N A V by E, or V is equal to I over N A V. And that V is drift velocity. All right. For those who get lost, I'm gonna show you again, right? I'll use back the same letters I have. Yes, yeah. I'm gonna show you back again. Some of them get lost. Right? So what you see? So I have A and I have L, right? So if I have A and L, I can find the volume here. So I know the volume there is equal to A by L. That's okay? Right? This N is something called charge density. All right? So if I were to multiply charge density by the volume, what I will end up with is the number of electrons or charge carriers. Right? And if I know the number of electrons in this circuit, all I have to do now is take the number of electrons and multiply it by E. And that will give me the total charge. Right? That will give me the total charge in the circuit. Right? Divish? If I know, yeah? For charge, no. Other than charge, you know, other things that remember, we could use this now to get current. Current is charge on time, right? So if I plug in the overall charge, I'll get NAL on E all over time. And I was saying that L on time is the average velocity that these electrons will take to go from here to here. Right? So L on T is what we call your drift velocity. Right? So you'll get I is equal to NAV by E. Right? And you can make V the subsequent formula.
I is equal to NEVA.
Yeah. Okay. That's one way to do it. And next way you can do it is start right here. Start with drift velocity is equal to length by time. Right? And you just kind of go backwards. And then we know that time is equal to charge over current flowing. Right? So then find the charge. Charge is the total number of electrons multiplied by the charge of one electron. Right? All over I. And then we can plug it in and we can solve for whatever we need. Right? So we can plug in for T and we will get V is equal to right? And you can flip it around and you'll get V is equal to L multiplied by I N T L. L will cancel. Same thing, right? Right, the only thing that you have to remember in scalar, the only thing you have to remember is what N is. Right? N is what we technically call charge density. Right? That's the number of electrons in a particular volume. Right, let's try this password for you. Right, so what we will do, what is left for us to do next day? Right, next day we'll do a couple of questions, we can, yeah. We'll do a couple of questions, like triple of the T, and then we focus on Kirchhoff's law, right? The next class, we really focus on Kirchhoff's law. Huh?